first one is going to be given by Guoliang Yu, and he's going to tell us about quasi-representations of discrete groups.
Well, thank you very much, Eric. I would like first to thank the organizers for inviting me. It's great to be back in this beautiful town. So I'm going to talk about quasi-representation of discrete groups. And I'm actually an outsider to this topic, but I have my co-author sitting in the front row, so if there's any question, he's going to answer for me. And okay, so let me first, say this is joint work with Shimo. So let me write. And Jiantao. G is, let's say, just a discrete group. So if I have a finite, this is a finite subset of G, and given a small positive epsilon. So a quasi-representation is just a map from this group to the unitary group, finite dimensional. It's called quasi-representation. Oh, sorry, that's from F squared, so it's just product of two elements. Well, let's assume that the identity is contained in F. So it's almost multiplicative. For all G and H in F. Okay, so it's a very natural, simple concept. Let me first give an example to see. I mean, at the first glance, you might think there's nothing interesting about this concept. So let me just look at an example. I think this was an example introduced by Cashdown and also independently by Kilasco. Take the group G to be the Z2, two copies of the integers. So we can just decide on one of the generators, say 1, 0. This is the unitary matrix. Let me say omega is the root of union. Okay. So this is the unitary matrix. And for the other one, it's just 0, 1. It's just a cyclic permutation. So this is an example of a quasi representation. And if you multiply them, you are just changing their position by 1 and take a difference with the original one. It's enormous. This is very small. Okay, this is a very interesting example. And now the central question for quasi-representation is the following. So this is a very basic. So when is a quasi-representation equivalent to representation? Okay, so this is a very basic question we are interested. Okay, so now this example it's just an example which is not equivalent to a true representation. Okay, so the goal of this talk is to provide abstractions to this question, and actually then try to classify all such a quasi-representations. That's of course a very ambitious goal. But before I do this, I need to explain what sort of equivalence are we talking about. And so there are quite many. So there are many different equivalence relations, but let me introduce the first one. And that's probably not the one which is studied in the literature, but in a way, at least to me, it's one of the most natural equivalence relations. So two quasi-representations, let's say Q0 and Q1, are called. Well, let's just call this homotopy equivalent. It's the most natural definition you can give if they exist homotopy of quasi-representations, which is just a family, continuous family of, let me use Q, of quasi-representation. So here T is from 0 to, okay. With the same epsilon, okay, such that Q0 is Q and Q1 is Q. Okay, so this is the first very natural and also kind of naive equivalence relation. I mean, it's clear this is an equivalence relation. But there is another one which is more studied in the literature. And so two quasi-representations, Q0 and Q1, are like unitarily equivalent. If they exist a unitary W such that if I conjugate them, it's actually not exactly Q1, but it's kind of small, smaller than some positive number eta. And so we use, so here we use the notation Q0 is homotopy equivalent to Q1. And here I use the notation that Q0 is equivalent, unitary equivalent to Q1, but up to a small error, eta. Okay. Now, this is like almost an equivalence relation, but it's not exactly transitive. For example, if I have Q0 unitary equivalent and 1 and Q1, Q2, then this will imply Q0 is unitary equivalent to Q2, but the error is slightly enlarged. Okay.
Definition 1, you require that the quasi-representation along the homotopy is with the same epsilon?
Yeah, the same epsilon. So let me just say F epsilon, the same epsilon. Yeah, that's a very important point. Yeah.
And in the second, it's for every element in F. What is the?
Oh, so this is also F. Yeah. The same epsilon and the same finite subset.
But doesn't triangle inequality leave the Q1 eta 1 plus eta 2?
Oh, this is it's when you apply this to, well, to be more precise, I think.
Well, yeah, he doesn't like the product of eta 1 times eta 2. That's, that's getting really tiny if they were both.
Oh, you mean eta 1 plus eta 2? Is this the question?
Yeah.
Okay, sorry. Okay, so this is like two different kinds of equivalence relation we will focus on. But I'm going to say they are almost equivalent. So my remark is that, so if Q0 is and then Q0 is homotopy equivalent to Q1, but I have to change the epsilon a little bit. As like epsilon plus, I believe, 3 eta, that's in our article. And I mean, the number has to be enlarged a little bit. Okay. And so that's the first remark. Second remark is that if two things are homotopy equivalent, then for any, no matter how small the eta is, and there exists another quasi and Q prime such that Q0, so just stably. So if I enlarge this Q prime, and that's going to be unitarily equivalent to with eta Q0, so stable. Okay? So we have to add another quasi-representation. So if we are willing to accept, like, classify things up to some stable quasi-representation, these two concepts are essentially the same. Okay? Now, before I move on, I should talk a little bit about history. Since I'm not an expert, so I might miss someone. Please let me know if I miss someone. So this has been studied quite a bit in the literature. Well, Cashdown, classical, of course, then, well, and...
Sorry, I don't understand the last notation, so there seems to be the same thing on the left and on the right.
Oh, yeah, of course, sorry. Okay, yeah, thanks.
But doesn't eta have to depend on epsilon?
Hmm? That's the same epsilon.
If epsilon is 1, saying that Q0 and Q1...
Oh, epsilon is, epsilon, normally we don't want epsilon to be 1. So epsilon is very small.
But eta doesn't depend on epsilon? In 2.
So eta is so for any very small eta. So we want eta, of course, so we want eta to be smaller than epsilon so we can preserve this. But actually you can, I think you have a very good point. So let me just, this eta, so I think let's just take eta to be smaller than epsilon. So just for comfort, psychological comfort.
Greater, maybe, no?
Hmm?
Greater? Or
Smaller.
okay.
Smaller. So it actually works for any, you can make it even more smaller. So it's not a problem. So the eta is the eta in this inequality. Okay, it's not in the, so the eta is this error. Okay, let me just briefly mention names. Alex, who is in the audience, and then Michel, he's supposed to be in the audience, and well, actually, together with in a different language. Okay, then. So, Marius, and my friend Carla. My friend Smo, of course, and my collaborate Rufus. Okay, did I miss anyone? Okay, so that's just some a list of people who has. I'm sure there are more people who has studied this problem. Okay, so now we have the right equivalence relation. So now, so essentially we want to classify quasi-representation up to one of those equivalence relation. Now, actually, this is a lesson from algebraic topology, and whenever we want to classify something or study something, we want to make it into an abelian group. Okay, that's what we are going to do next. Okay, so this is already suggesting that we should add two things, like this is equivalence relation. So the way to add is just okay, and this is. Up to this equivalence relation, this is abelian. Okay, so this is like this. So this is an abelian semigroup. So let me use this notation. So this is the abelian semigroup of all.
guess your norm is always the operator norm.
Yeah, I'm the operate norm right now.
So
Yeah,
otherwise the sum does not stay. Okay.
yeah. So I'm using the operate norm. Other norms, it's also of course a very interesting question. So, but so far it's operate norm.
And the bracket refers to which equivalence
Uh,
relation?
It could be any of those. So essentially they're equivalent. These two equivalence relations, they are the same. If we allow a small error. Okay, so now there's a standard process of turning an abelian semigroup into a group. That's the quadratic process. Okay, so that's what we do in casing. Okay. This is the abelian, the quadratic abelian group from the semigroup. Okay, and so we are interested in computing this group. Okay, so it turns out the most effective way of doing this is by introducing a character map. That's pretty much like in classifying group representations, especially finite groups. Okay.
So this has, if I fix f, epsilon, and n,
Yeah.
then there are only finitely many equivalence classes, right?
Oh, n, which n is the dimension.
Yeah.
So we are not fixing n.
No, but my question was if I fix epsilon, f, and n, then there are only finitely many equivalence classes, right?
Yeah. Yeah. If
In a sense, you can organize this into a semi-algebraic set, and then there are only finitely many equivalence.
yeah, you can do that. Yes. Yeah. Okay, so we are going
By the
to.
way, I mean, when you do that and then you use a Loyasevich inequality, right? I mean, it tells you that there's some relation, some kind of stability, you know, for an epsilon that depends on n, you can always see that epsilon closed things are really representations. The real problem is when epsilon is fixed and you're not letting it go. Epsilon is going to be fixed and small, right? I mean, because if epsilon is if the epsilon decays with n, then Loyasevich inequalities tell you that everything will become approximated.
Okay. All right, so because this group, you know, it's from the way we define it, it's not very computable. So now we will try to make it computable by defining a so-called character map. Okay. So the character map is so roughly speaking, it is from this to the K-theory, which is just about equivariant vector bundles. Okay, so G of some universal space on which the group acts. Okay, so the universal space is it's the Lipschitz complex. Okay. Let me just call this E is a Lipschitz complex. This is. So to be more rigorous, so for any, so what is E? E is a finite subset. So this is a finite subset. They exist like another finite subset G and epsilon. So the F and epsilon depends on E. The size of F is roughly the same as the size of E. Okay, so what is the Lipschitz complex? Then we just, so this is just the simplicial complex. With all the group elements with vertex as its vertices. And a bunch of group elements G0 to GK spans simplex if and only if they are like close by, measured in this final set E. Okay, so that's, I guess, most of us are very familiar with. I mean, normally we use like a distance on the group to define this, but I want to avoid the use of distance, but it's equivalent. Okay, is this board visible? Probably not.
Yeah. There's less than half, just the upper half, but then you can.
Oh, the upper half. Okay, I'm not tall enough to use the upper half.
You understand the statement, for every E, there exists F.
Yeah, and epsilon. Epsilon, we need the epsilon to be small enough.
Yeah, but such that, but now you wrote PE.
Oh, such that this can be defined. The character map can be defined. Yeah. So to define this, we choose an E first, then choose an F, which is large enough, and epsilon, which is small enough. And F is roughly the size of E. Okay, we can, if we want to forget the detail, we can choose F to be the same as E, but it's a slightly big.
So F has to at least the generating.
Well, actually, I'm avoiding talking about generating set because the group, I'm actually having the flexibility, the group is not necessarily finitely generated. But you can focus on, yeah, you can use that as one of the generating set. That's okay too. Okay, so let me just motivate this construction a little bit. So in the case, if Q is a representation, then this construction is very intuitive, okay? So, so then I can just, so this has a natural G action, of course. So if it's a true representation, then this, of course, this is, of course, it's a vector bundle. It looks trivial, but it has a diagonal action. Okay. So diagonal action. Of G. So that with the action, often it's non-trivial. So the group G acts on the Lipschitz complex naturally acts on Cn as a representation. Okay, so in this case, psi of Q is just this vector bundle. Okay, as an equivalent G bundle. Okay, as a G bundle. So it's a very intuitive kind of construction. Now, in general, our action on the Lipschitz complex is, of course, a so-called proper actions. It's not necessarily free. In the case it's a free action, it's very well studied in the literature. But for us, the subtle point it's a proper action. It can have non-trivial isotropic group. So actually we struggled for a little while how to define the character map. I think the classical way, at least, I don't know how to make it work, by using skeletons, like by an induction. But this is where we use a little bit of algebra. So instead of defining a bundle, which probably can be done, but I don't know how actually. And we use the algebraic characterization of what is a vector bundle. And so just like in algebraic K-theory, so a vector bundle corresponds to a projection, okay, in certain algebra. Now, since we are talking about equivariant bundle, so the right algebra is some kind of cross product, okay, which I'm going to introduce now.
Maybe it's worth saying what happens when G is finite, right? When G is finite, what you're trying to do is you're making use of the fact that every almost representation is almost really a representation, and that's what the vector bundle over a point is.
Yeah. So,
Right,
so
so
Shimo has a very good point. If the group is finite, then every quasi-representation can be made into a Q representation. So therefore, essentially the same construction still works. Okay. All right. So now I'm going to use a little bit of algebra. Okay. So this is, let me introduce the cross product algebra. Okay, so the first algebra is all the continuous functions which vanish at infinity on this space, okay? Now, this, as we saw, there is a natural action, so form the cross product with G. Okay, so this is, what is this? It's just formally, it's a finite. Let me first do the finite thing. So G is, Fg is just a function, continuous function on this space, which vanishes at infinity. Okay. Now, how do I multiply two things like this? Fg, G, for example. Okay. So we want this algebra to encode the action of the group G on the space. So it's like, you know, we meet many friends in the hallway. When we cross by, we want to say hi. Okay, so which means that, and so the way you define it is you want to have G acts on this, and then just multiply. Okay, so this is a cross product. Okay, it's the most natural product that you can define by, and this way you encode the action of G on the space in the product. Okay, now we also want to, well, this is just complete this. Okay, all right. So what is nice about this is that if now I'm going to talk about equivariant K-theory, which is just the group, abelian group of all vector bundles on the space. This is just going to be the K-theory of this cross product. So by K-theory, I just mean the abelian group generated. So this is just the abelian group. Generated by projections in the matrix algebra. Okay. Now the way vector bundles correspond to projection is that because vector bundle, there is always another vector bundle whose direct sum with it it's trivial. Okay. So the projection is essentially just from the trivial bundle to the sub-bundle we started with. Okay, so that's how the projection is. With correspondence. Now with this, actually we can write down the projection, actually it's a very clean formula. When I have a quasi-representation. Okay, to do this, I first choose a cutoff function. C. Okay, so this function, first of all, this function is like, it's a continuous function, and whose value is between 0 and 1, and it's compactly supported. So, I mean, roughly speaking, it's supported like along the fundamental domain of the action, okay, intuitively. Now, when you translate all this function by all group element, and this gives you 1, okay, for all. Okay. Now, the projection, okay, so this projection P, we can literally write down a very clean formula. Okay, so this is G C X, the cutoff function, and the group G. That's the thing in the cross product. Then the quasi-representation. Okay. Now this is a finite sum. Okay, because there are only finitely many G for which this product is non-zero. Okay, because when you move G like very far away, this is G inverse X. This would not intersect. It's not on the support of C. So then it's 0. So this is a finite sum. Okay, you can easily check this is a projection. Oh, sorry, I lied a little bit. You can easily check this is a projection if a Q is a representation, and it's the same bundle we talked about here. Now, so in general, this is a it's not a quasi-projection. If Q is a quasi-representation. Okay, now, but if it's so what does that mean if it's a quasi? So it means that, to be a projection, the square should be 0. But in this case, this is very small. It's very small. Depends on epsilon. Okay, very small. But that's something, like Erika and I, really like, because that's in operator case here. There's a lot of stability. It's almost something we can make it exactly something. Okay? All right, so actually you can do a so-called functional calculus, okay? And remove the things which make it small. Then you get a projection, okay? So the projection we really want, let me call this P prime, is some kind of functional calculus. And so F is just a function like this. So when it's small, it's 0, then it turns into 1. Okay, it's a function like this. This is F. Okay, this is a real projection. Okay, so we are taking advantage of like something in operate theory, in operate algebra, and make it a projection. Okay, so now I'm ready to define. So maybe I just define it here. Okay, so character. Side of the quasi-representation is going to be this P prime. This will give you the vector bundle. It's the equivalent vector bundle on the Lipschitz complex. Okay, so here I raise one problem. I don't know how. I mean, can you do this like topologically? Well, this is a question for Shimon probably. And so actually, this is a very simple construction, but we struggled it a little bit. It took us like a couple of months to figure this out.
So can you just say something about this quasi-projection? Is this central
Hmm?
Is P central? Well, what kind of function you take on the spectrum of P?
P. Oh
Oh,
yeah.
that's what he was trying to draw, that kind of function.
Yeah. It's a so P is
The
if
spectrum is, right, it's like near 0 and near 1.
Yeah.
Right? So then you just want to remove
yeah.
the stuff that's away from 1 and make it, you want it to be constant, say near 1.
But
And die away from there, and then that fixes it up.
But if you're worried about self-adjointness, we can make it self-adjoint because this is almost, this is also small. I mean, if you wish, instead of considering P, I can consider, it's adjoint and the average with itself making it self-adjoint. Then, but actually, this is not necessary to do the functional calculus. And but well, of course, we feel much more comfortable with a self-adjoint element.
Yeah, by the way, there was this guy, Benedict Unger, who I think, in the case where there's sort of, right,
It's a free action.
Right, when it's a free action,
Yeah.
then basically what you're doing is you're using clutching functions concretely, and you're producing a non-flat bundle. If you had a representation, you'd be doing the flat bundle with that holonomy. And here what you're doing is you're just saying you introduce a little bit of curvature, to handle the epsilons.
But I think his definition involved like an induction on the skeleton, right?
Yeah, so you run into trouble if you had infinite dimensional ones.
So Hunger, I should add his name here. So Hunger has this construction, and Maris also has something similar, but they all depend on some either coordinate or induction by skeleton. So I don't know. I don't know how to make their construction work in this general case. So, but we can write down like some map like this. It just in very clean formula. So this is the formula. Okay, so now. Okay, so what are we doing here? So we define this character map. And so this abelian group of all quasi-representation is a mysterious object we try to understand. But K-theory is very well understood in many ways. And so for example, there is this theory of Baum and Kahn. Baum and Kahn, they define some chain character from a space like this to some cohomology, so some even dimensional. It depends on how much time I will have. I will try, if I have time, I will explain this in more detail. Okay, so equivalent homology. And this is an explicitly defined map, and this it is rationally isomorphic. So I'm just trying to emphasize this is at least rationally, it's very computable. Okay, we know how to compute this. Okay, so now here I'm just going to I can compare this. So these two groups, and I want to say they are basically the same group. Okay, but I don't know if this is true in general. So we are going to make a conjecture Shimo, are you comfortable for us to make a conjecture like this?
Yeah, but I don't feel when I make conjectures that they have to be true.
Yeah,
Okay?
it's a problem.
It's something to stimulate discussion.
Yeah, exactly. I believe in general it's not true. But I don't know of a counterexample. So well, maybe because Shimo gave a very diplomatic answer, so I'm just going to say conjecture problem. Okay. So Kasai. Now because E and F are kind of changing, so let me just make to make the F kind of go away, I can take the inverse limit. We can also make some kind of quantitative statement without the limit, but just to make life a little bit cleaner. So this is an isomorphism. I'm varied some a little bit details. This epsilon.
If epsilon is small enough or what?
Yeah, actually, this epsilon. Yeah, exactly. That's a good point. That's what I was going to say. So epsilon F is also going to 0. Yeah, it's small. This epsilon actually depends on the size of F. This is a very good point. You see, why do we need to make epsilon small? Because it depends on the number of terms G here to make it a quasi-projection. You can see like the number of G here is basically the same as E, but with maybe multiplied by the generating set. So enlarging this a little bit. Okay, so So let me first tell you what we can do. What we can do is the following. Okay, so if the group G is kind of small, is amenable, then the character map is an isomorphism. So this is what we can do. The proof is a little bit technical. We are trying to make it less technical, but so far, yeah, it's a little bit technical. Now, for general,
The Kashtan stability for amenable group is a special case of that. It follows from that, or it's a different type of stability.
so that's a question. Actually, I'm not very familiar with.
To be honest, it's a while since I looked at the papers. I don't think
Kashtan proved that if you
Right.
have an
but his was uniform over all the elements of the group, and here we're using a generating set. So I think it's
no,
not.
I know that it's a different, but still.
Yeah, I'd have to think about whether it doesn't seem immediate to me that it follows.
But his result, does his result say it's trivial, everything? For if it's defined on the whole group.
Yeah.
Right.
Okay, so even for our example, Z2, it's not trivial. So let me also just point out for the initial group example, and the character map, the character of that quasi-representation, like in K-theory, essentially gives the non-trivial generator, because for the in that case, it's going to be the K-theory of the two-dimensional torus, and which has two generators, one comes from trivial bundle, one from the top dimension. So that element actually gives you the generator on the top dimension. So that indicates it's a little bit, it has more examples than the Cashidon's result, because his quasi-representation is defined on the entire group. Okay, so that's just in the amenable case, and now in general, this construction gives us some obstruction. So now probably I should talk about what this group is. So this group, this group is actually all the sum of all even dimensional. Let me first write this down, then I will define the head, so-called. Okay, so what is the head space? This is just all G, X. G is in G, and the X, of course, in G. X, these are all fixed points. Okay, so if G is identity, of course, this is just the entire space. And but in general, because the action is proper, then so G is in the isotropic group of X. Okay, so now G acts on the head space, so by the following, so Gx, so G H. Okay, so this is a natural action. This is the quotient. Oh, let me just using the rational coefficient. So in general, our construction is that if the quasi-representation is equivalent to a representation, then the chain character of the character of the quasi-representation is contained in the image of the inclusion map. So the inclusion so it's the zero-dimensional component. I think rationally, this is essentially, if the conjecture is true, is true, then this is rationally is an if and only if condition.
If and only if or no?
Rationally, yeah. Rationally, if the conjecture is true. So it means, you can see in the cohomology level, there are not many quasi-representation which is equivalent to true representation. So the true representations are zero-dimensional stuff. Okay, so quasi-representation in general, if the conjecture is true, it will give you all the high-dimensional stuff. So it's much more rich. So it's so this is telling us the theory of quasi-representations is very rich. Okay, although at first glance it might be most of them should be true representation, but this is telling us, yeah, most of quasi-representation are not equivalent to representation. Shimo, you have a comment?
Yeah, and firstly, the evidence for surjectivity is much better than the evidence for injectivity. Okay, so that's one thing to keep in mind.
Yeah, that's true.
And the second thing to think about is that, you know, very often people will look at, say, term characters of almost representations, and this description has more when your group has torsion, right? Because the cohomology of the centralizers of the elements of finite order are also present here. So you get extra term classes associated with those.
Yeah, yeah, those are very good points. And yeah, I should say this conjecture is very strong. If it's true, then the Novikov conjecture is a consequence of that. So that's already indicate, you know, it's a very strong but conjecture. Yeah. Yeah, but as Shimo points out, actually we know much more than the surjectivity than the injectivity. Unlike this is in a way it's the due of the Novikov assembly in some sense. So it's not surprising. So yeah. Okay, that's all I want to say. Thank you very much.
You know, to say something about groups which are not amenable, I'm particularly interested if you take lattices in iron periodic group and by Guoliang the cohomology vanish. Does it mean something? Does it get something?
So for the second part, we are not assuming anything. So if we are going to just interested in obstruction, then there is no condition. So amenability is only on the first theorem. Now I think so. This we have not checked the detail. I think, you know, for example, if you have a group which is amenable or H group, it's residually finite. The same. Well, even for the first theorem, it should be still true.
Then what?
Oh, if it's like amenable, it's like surface group, or like, and also residually finite, then the first results should still be true. Although they are not amenable. But so one open question we have is for hyperbolic groups. We don't know if the first theorem is true for hyperbolic groups. And that's actually, this project started during COVID for over many years. And Shimo and I.
The opposite case, Guoliang property T, you know, if it's very rigid group, like, and let's say cohomology vanish.
No, but for example, I think that for linear groups, right, I think it should be okay.
For linear groups,
Right,
for
the
surjectivity,
surjectivity.
is not a problem.
Okay, yeah.
Subjectivity is not a problem.
Subjectivity of that map.
Of that map, right? So,
Yeah.
right, so there are lots of elements, and then if your linear group has elements of finite order, then you can get around the absence of cohomology. Right? So if you would design something where Guoliang doesn't predict anything even, but you find an involution inside where its centralizer has the opposite cohomological dimension, then you would be okay. I know what you're thinking about that.
Yeah, you know.
You're pretty transparent.
Yes.
So the second theorem, I think, it can be seen as an obstruction to being stable in this sense for the group.
Yeah, it is an obstruction.
How does it compare with the obstructions that Dadarlat had
Oh, okay. So I think that's a good question. So data loss, it's like free action.
It's what?
It's the action is free. So let me just compare. This is a good question. So if if G is torsion free, let me put it this way, torsion free, then in this case, this group H even of PEG, let's see, G. This group is just H even of the quotient. Okay, so this is, yeah, so then it coincide with Marius' case.
All right, so I propose that we can continue the discussion in the coffee room. The next talk will be start at 11:45, and let's thank Guoliang